Calculations of standard enthalpy of formation are some of the more straightforward ones because the equation is given, delta H equals products minus reactants, and the values are given usually in a very easy to follow table form. So here we have a table with lots of values. When given on a problem, when given even in a lab, or especially an AP question, they're much simpler. In a multiple choice, you wouldn't even go to this many decimal places likely. In a free response, you might go to the ones place or even the tenths place. The difference from bond energies, once again, is that it's products minus reactants. So I've got these values, which I plug in right here, accounting for the mole ratios or the coefficients. I've got these values over here. And if you tried to find oxygen on this chart, you may have spent a very long time on there because oxygen gas is an element in its natural molecular form or its natural elemental standard state. It does not have a value or it has a value of 0. This is a combustion reaction, so we could predict that the delta H is negative, and the value obviously does come out to negative. We get negative 802.3. And hopefully we remember if there's something where a one does not come out negative. In fact, when I was initially solving this problem, I had my values in the wrong places. So trying to connect with other parts of the problem or information that you know is very useful. The same idea down here. We're just adding up our products, subtracting our reactants. Here we have a few elements in their natural state, magnesium and hydrogen both. One thing to note as I was doing this chart for some reason did not have HCl aqueous, so I kind of cheated and put HCl gas. You would have to be given the exact value, obviously. You could, if given your delta H, be asked to find the heat of formation of a specific substance. That is a common problem as well, but a little bit less common than what you might see with the bond energy as we did previously. This same equation carries over to other thermodynamic data, to entropy, to free energy, and to enthalpy, as we just did. So you'll see this a lot and apply this a lot, but also take the answers that you get from this and use them in other parts of a calculation as well. When we think about these values, everything that I used was either a value of 0 because it was an element or a negative value. That's because each of these compounds is more stable than the separate elements that it came from. That's very common, and on that table, most common compounds have a negative value for a heat of formation because many are more stable than the elements they are made from. That's not true of all things. The positive value indicates that that compound is maybe less stable than the elements itself, or more correctly, that it requires energy to make that from there. So that positive and negative value doesn't just have a numeric meaning, it also has a meaning that's tied to the stability or to the energy that is exchanged throughout the process.